Hello and welcome to this video where we will be now looking into the 2-qubit circuits. Up until now we have seen single qubits, we have seen gates which are operating on a single qubit, the Hadamard's, the poly X gate and the poly Z gates. But in reality, the circuits are, of course, much complex than what can be represented by single qubit. So just to give you an idea about what the complexity can entail, we are looking into 2-qubit circuits. Just in case of classical computing, which is represented by bits, 2 bits will represent 4 state 0, 0, 0, 1, 1, 0, and 1, 1, 2 raised to the power 2, 4 states. Similar logic can be applied to qubits as well. Here, of course, the difference is that these are the quantum states that is being represented, and it has a special way of writing, as we have seen all along the way, in terms of bracket notation. So 0, 0, 0, 1, 1, 0, and 1, 1 in a bracket notation. We can also write this a bit differently, and they are all same, or rather equivalent, and quite interchangeable. So this is something very important to note. So 0, 0 can also be written as the cat 0 and then cat 0 again. Similarly 0, 1, 1, 0, and 1, 1. You can also write this in terms of the Kronecker product that we have seen in quantum linear algebra, or the tensor product as the most commercial name is, and it is represented by a circle marked with cross inside it, as you can see clearly here. So all this notation, I repeat once again, are equivalent to each other, quite interchangeable, and that is something quite common in when you do an actual circuit design, that these are used quite interchangeably. So it is good to have a grasp of this one, quite handy. Some of the conventions are more directly used than others. So for example, what's been represented here as marked in the green color is quite interchangeably used. So if you know about this, your way of calculating and designing circuit would become much more intuitive and much more explainable to you. So as I said, the 2 qubits can represent the quantum state, a combined state, and it can be represented as the Kronecker product that we have seen before, its equivalent. We can also write this in the vector form, because a qubit can be represented in the vector format. Here you see 0, 0 is been represented in the vector format of 1, 0, 1, 0. We apply the Kronecker product, and when you do the mathematics of it, you will get the state, again a vector state of 1, 0, 0, and 0. You can extend this logic to all other combinations that we have seen, and you can do the mathematics on your own, and you will find the exact result what you are seeing here, extending further to 1, 0 and to 1, 1. And these are again the vector representation with one attribute pointing to 1 because it's normalized, and all others are 0. Now, if you look this into an actual equation, if you have a superimposed state, as you can see on the example here, you can actually extend this mathematics quite easily on this and see how it pans out in terms of the actual final combined state. As I said before, the states can be written interchangeably in the conventions that we hear. Same here. What we can do here is that we take the vector states and do the combination of 0 and 1, and then write it in terms of the format where we can apply the Kronecker product. So the vector state of 0 and 1 will be 1, 1, because 0 and 1 both are represented as 0, 1 and 1, 0. And when you combine it in a vector format, it becomes 1, 1. And similarly on the right hand side. We then apply the basic mathematics or quantum linear algebra. Take the scalars out, 1 by under root 2, and when you multiply, you get half, and then the product of Kronecker product of vector 1, 1 with vector 1, 1. You expand this mathematically, and what you will see is that 1 half of a vector representation of 1, 1, 1, and 1 can be further broken down quite easily to the constituent state of 0, 0, 0, 1, 1, 0, and 1, 1. And remember, this is still L2 normalized, which means when you take the square of the probability coefficient, it will become 1 by 4, 1 by 4 times 1 by 4, plus 1 by 4, plus 1 by 4, plus 1 by 4, 4 times it will give you 1, which is what the square of probability coefficient should give you to it to be a valid state. This actually presents a very defining picture, so to say. So you see that you are expanding a superimposed state, and you get to an expanded format, which you can also trace it back and go to the composite state. So both the expansion and decomposition is possible. One is from input to output, other you can take it from output to input. You can then, for example, take another example to have a tensor decompose a tensor product. So if you have a state like what's written here, and remember you can use the convention interchangeably, you can write it down as this. And when you continue further, you will see from input to output is an expansion of the state, and from output to input tracing it back, it becomes an decomposition. So what I'll do is that I'm going to stop here. It's best that you practice this, probably handwritten, to get the idea. But this has to be very, very clear, because when we go into the actual circuit building and logic, the changing conventions and playing around with the conventions will give you a lot of leeway in trying to understand what is actually happening. If this is not already very intuitive to you, then as I said, please must try, probably handwritten, to get the gist. Thanks for listening, and I hope to see you in the next video.